Hello, everyone, and welcome to this Industry Tech Days 2021 Fireside Chat with Power Integrations. My name is Kate Smith, and I'm the editor-in-chief of All About Circuits. And apologies for the late start. We just had a little bit of a hiccup with the technical details, but we are up and running now. So if you're making sure you're in the right place, today we'll be having an in-depth chat about GaN, and it's all about efficiency. So we'll be talking about small footprints, particularly the ever-important combination of saving energy and reducing physical size. So here with me today is Doug Bailey, the Vice President of Marketing and Applications Engineering at Power Integrations. Hey, Doug, welcome to Industry Tech Days.
Hi, Kate. Thank you very much for having me.
Well, before we dive in, let me just get a few things out of the way here. The first of which is that for everyone in the audience, if you look at the bottom of your screen, you'll see a Q&A widget through On24. This is how you'll be able to submit questions for Doug, and you can submit them at any point in time between now and when we end the session, and we will end the session with a live Q&A. So this is a really great opportunity for you to have like real-time conversation with someone of Doug's caliber. So I highly recommend you take advantage of that. Secondarily, at the end of the session, we're also going to name a giveaway winner, so stay tuned for that. And finally, the slides will be available on demand for this presentation, and the entirety of the recording will be available as well. So with all of that aside, let's get going, Doug. Today, our focus will be on efficiency and power. Where shall we start?
The title of the topic is the gallium nitride. We've been very successful in rolling out gallium nitride within our product line. It's had excellent feedback from the market. And what I thought we'd do is go through a little chat about how we did it and what benefits people are getting from it, and really more take a look at it at the higher level as well, perhaps some of the societal benefits or observations that gallium nitride has, some of the perhaps surprises that gallium nitride's served up for us here at Power Integrations.
That sounds perfect. Let's get going. All right, so let's talk about what efficiency really means. I think this is a really interesting first slide that you've chosen here. And a lot of people in the audience are probably thinking that this might be a straightforward definition. So what is it about this conversation that we're going to be having that makes this a trickier concept than it maybe first appears?
Well, I think a lot of people focus on efficiency and maximum power. And that's very, very important when you're talking about something like an adapter, because you're thermally limited in a tiny box, right? So you're trying to put your power supply in a tiny box. You're thermally limited. And so efficiency at maximum power actually dictates the form factor of your solution. And so that's one way of looking at efficiency. But there are other places where efficiency matters, and that's in a situation where you're not always running at maximum power. And there's actually another slide here where this is an example. It's a robot example, but it could really be anything. Most systems don't operate at peak load very, very much. Primarily, they operate at light load. And so it turns out that if you're trying to manage energy waste at a sort of more general level, full load efficiency isn't really where you want to focus your attention. You want to focus your attention on what happens during normal operation, and that's why a lot of the regulatory activity through the Department of Energy and through the Chinese regulatory agencies, the European regulatory agencies, that they're focusing on energy use of systems across the load range rather than simply the peak efficiency, because they consider the peak efficiency to be more about desirability of the product and less about saving energy.
Mm-hmm. Can we talk a little bit about this particular, on this slide, this example that you've set up? So we're talking about peak load, moderate load. For this particular application, what do those loads look like?
Well, this is a robot. A robot is I don't actually know what kind of robot it is, but it's moving material around, and so when it's engaging in an acceleration phase or a braking phase, you'll find that it's using more energy than when it's stationary or quiescent. And so those are the times when the motors are under load, and that's when the peak load is going to happen. Turns out a lot of things are like this. Printers are like it. Most of the time, a printer is at relatively light load, and then you'll need to sort of line feed a sheet of cardboard, and these big motors have to really work hard to move, to bend something around the rollers. It's the same with computer systems. The computers are at relatively light load while somebody's thinking about what they're going to type next. But when they're playing the video game, they might be at full load. So there's a very wide range of loads in most systems. Even lighting, where you think, well, you turn the light on, you want it at full power. But a lot of the time we use dimmed lighting. And so when something's dimmed, you don't want it to be dimming by throwing away the excess energy. You really want it to be dimming by not using the excess energy, the extra energy. You want it to save it. And so most power systems are not operating at full load.
Mm-hmm. That makes a lot of sense. And in this case, just so everyone sort of is following along with the example, what are those power-hungry subsystems in this particular example? Just are we mostly talking about?
This is the motors. Yeah, this is just the motors that are driving the robot around. I have an example of this is a power curve of a typical PWM controller. For example, we're going here from about 5% load up to 100% load. You notice the efficiency is tuned for peak load, and so the chap who designed this power supply was thinking, okay, I've got to get this in the box. This is a thermally limited scenario, but in order to do that, he pushed the efficiency way up into the full load range, rather than spending a lot of time optimizing efficiency, where the system might actually be operating. So this is one where perhaps it wanted to be pretty or small or compact, and in order to do that, sacrificed energy in the normal operating range. So we don't like to see this, right? This is a little bit of a sort of 2000s kind of power supply design. It's not necessary anymore. There are techniques that you can use that provide a very flat operating range.
And just out of curiosity, when you're talking about, obviously that's not what we want. So that graph that you have on the last slide, when a designer, if we put ourselves in the shoes of this designer who is putting together a system, they're assessing, they're characterizing the power usage for this robot, when they see that original power usage and then they see optimized, are they typically immediately thinking that, hey, this is an opportunity, this is something that I can optimize towards more? Or what are the first steps when you realize that there's this much inefficiency going on in a system?
Well, most engineers are pretty responsible people, right? And so they're not designing deliberately to waste energy.
Sure.
Engineers just don't think that way, right? We're trying to optimize all the time as well as we can. But sometimes you get trapped into a situation where there's a specification that you have to meet, and I can interpret from this slide that the engineer who did it was interpreting or was being asked to do more efficiency or tune the circuit so that it was efficient at the high end. So something like this, he may have had to use a very much lower RDS(on) transistor than he really wanted to, or he may have had to operate at a higher frequency than he really wanted to in order to get the power out. And so that will have created this unfortunate inefficiency at the lighter load levels. So engineers they're not going to waste energy on purpose. They're far smarter than that. but sometimes you just get trapped, and you have to use some other techniques, or you should educate yourself on how to use other techniques.
Sure. So maybe that first step is that self-education. And just to summarize, basically what you're saying is that we really want to maximize the amount of work a device can do in its lifetime while minimizing that wasted energy.
Yeah. So you have to forgive me because I'm going to use one of our products as a demo because these are the ones I'm familiar with. But I realize this is not supposed to be too dedicated towards any particular product line, but this is a realistic solution that we have. This is a demo board, 45 watts, so 20 volt, a little bit more than 2 amps demo board. It might be used it's an open frame design. It might be used for something like an appliance, maybe the bias supply for a refrigerator or something with motors in it. It's a very typical appliance type power supply. And when you're in something like a refrigerator, your motors or your motor drivers, which is what's using the energy, if it's using a brushless DC motor, are not operating at full power all the time. The full power would only come when you first turn the refrigerator on and it's hot inside and it's going through what is called a pump down cycle. But there are many other places where you almost never use full efficiency. And if you look at this power supply, it only starts to tail down a little bit, and I'm talking a little bit, going from 92% to 90% at 20% load and below. So this power supply, is pretty nice. I mean, it is almost flat in efficiency, and not only is it flat, but it's flat and it's high efficiency at the same time. It's in excess of 92%. At 115 volts, and then you'll see at 265 it drops down a little bit. I think that's is that the 2? No, maybe that's a 90. Yeah. So at 90 VAC, it's a little bit lower than that, but that's more of a thermal concern rather than operating the sinks. Most of the time you'll be operating at the 115. So the use of energy is spectacularly good in this particular design. Mm-hmm.
Well, and just for some context, can you just very quickly, what type of converter design are we talking about with this linear switching bus?
Oh, this is a little flyback. So if you look at the back, we've got this chip here. This is our chip, actually. It's the one we're proud of. This bridges the isolation barrier. It's got the primary on one side with the main power switch and the secondary on the other. And then there's a magneto electrical link between the two, a couple of cross bond wires that allows signals to go from primary to secondary to primary, but they're isolated, so they're safety isolated. We test all of these things at I think there's in excess of 4,000 volts in final test put across this thing to make sure that the isolation is safe. And then it's got a little flyback controller and a synchronous rectifier controller built in. And that's really the trick, is getting the synchronous rectifier and then the flyback main switch working nicely together so that they do a good job of maximizing efficiency. And I don't know how many sort of super technical people are on the call, but there are two ways to run a power supply. There's a discontinuous mode and continuous mode. And part of getting the very nice efficiency across a very wide load range and a very wide line range, because we went from 90 to 265. So you've got a very wide operating range, is to be able to work in both continuous and discontinuous modes. And that is really only possible when you've got a very positive and reliable link between the secondary and the primary of the controller. Mm-hmm. So this is a nice little chip we sell. We sold up sort of 1 billion or more of these over the last few years.
Right. And you're in good company. Our expectation is that most of our listeners here are going to be able to follow along just fine. So let all of that rip, please. And before we move on here, let me just, if I can here, when we talked about a higher level, sort of part of this conversation. So on this slide, you're saying that energy standards just can't keep up. So in the past, what has that relationship with energy standards been like? Have they impacted the way that you guys at Power Integrations see the market? Have they challenged you and driven you forward in the past, and now you've just sort of moved ahead of them because they're just evolving too quickly? What's the situation there?
Yeah, so I think the energy standards guys have a very tough job on their hands, because on one hand, they're being asked by society to affect change, right? To mitigate the climate change problem. And then, but they don't want empty shelves, because ultimately they're responsible to politicians, and politicians are responsible to voters, and voters don't want to see empty shelves at Christmas. So they've got to walk a pretty delicate line where they edge up these standards over time. What we're doing is we try to always exceed the standards that have been put in place. And that's because we believe that energy efficiency is important and societally, and we also believe it's important to our customers, and we feel like it's a trend of the future anyway. And so by being the most efficient we can be, we're always on the leading edge of that mega trend towards being more efficient. So that's just a strategy we put in place, and it's served us very well over the years. But what it means is that we're actually ahead of the regulators. So I would put here energy standards can't keep up, but I don't want to make that seem quite as pejorative as it says. Right? It's phrased a little negatively, but that's not really what I meant to say. What I meant to say was that they don't keep up because it's not in their nature to do that. They're trying to save energy, but they're trying to set a floor. They're not trying to set a ceiling. They want to they want to make sure that it's a level playing field for everybody. So that's why it has, these standards actually have utility for the systems vendors, because if people can cheat and use lousy product or really, really inefficient power supplies going direct to sort of line frequency transformers or something like that, it's horribly inefficient. They waste 70% of the energy that goes into them. But people might use those if they could save a few cents, and the market is competitive, and so people might do that. So what the energy standards are doing is they're setting a floor, and that provides a kind of an agreement where nobody's going to go below that level, because it's just not the done thing. And also you may not be able to sell your product in certain areas, or you may have to stick a label on it that isn't very friendly to your marketing goals. Or so the different agencies take different tactics on how they enforce or encourage the use of the standards.
And honestly, you've been much more empathetic towards the standards guys than I think I've ever heard anyone be before. So don't worry too much about that. It's a very positive message. And just very briefly here, when we're talking about, I feel like it's worth mentioning here that we're talking about on the slide here, up to 95% efficiency. Basically, 100% efficiency is theoretically impossible, right?
Of course.
Do you envision us wrestling with climbing up to 96, 97, 97.5, 97.75? Because it seems like the curve of progress, it's kind of asymptotic to some extent, isn't it? It's infinitely closer to the theoretical limit, but it never quite reaches it.
Yeah, so in one way you'd say, well, we improved it by 1%, and is that our life's work, and how 1%? But that's not really the right way to think about it. The right way to think about it is that if you're at 90% efficiency, for example, and you improve by 1%, you've reduced the losses by 10%. So as you asymptotically approach 100, every little bite you take out of it might sound small in percentage terms when it's set against, as you said, 96, 96.5, right? It sounds small, but it's very large in terms of the amount of losses, and that allows you to squeeze the power supply into a smaller space if you're thermally limited, or just save energy, right? Which is, I think, a reasonable goal in itself. So in terms of where we're at, this is a simple flyback, but there are other topologies you can use. We have a new product, the 4th generation of this Nswish device that has something called an active clamp, and that was an observation that the topology flyback has a nasty little property of burning its leakage energy, so that every transformer has a little bit of leakage, and it burns the leakage energy. So, but if you can recover that and feed it back into the system, that you get that back. And we're now pretty routinely building flyback power supplies, active clamp flyback power supplies, in the 94 to 95% range. Mm-hmm. So then you got to look at, well, where's the next ugly thing that's burning energy? And it turns out it's the diode bridge. So that's the kind of, I don't want to say that's the next target, because I don't know how to solve that one, frankly, but at least not in small power supplies efficiently, but cost effectively. But that's the hog, that's the pig on the board, is the diode bridge. The power converter, if you take the bridge out, is already in the very, very high 90s.
Mm-hmm. And I was actually sort of expecting you to also mention there, speaking of the next new thing, I think, we can touch on that next. People showed up to hear about GaN. Let's talk a little bit about GaN.
Yeah, yeah, we haven't talked about GaN, have we? There's all the text that I talked to and never clicked on. But all right, so let's talk about GaN. So the GaN is much closer to being an ideal switch than a bipolar transistor or a MOSFET. So bipolar transistors from 30 years ago were pretty poor, but they did their job. Then MOSFETs took over and they did their job, and they even superjunction MOSFETs are better than the standard planar MOSFETs. But every one of them has these parasitic properties, and mostly related to capacitance. It just turns out that if you remember your EE 101, right, the capacitor is the epsilon A over D is the equation for capacitance. So it's divided by the distance between plates, and it just turns out that microchips are very small and they got very thin isolation. And so the capacitances can be quite high between the various lumps of metal or poly that make up the transistor. The property of GaN that makes it so special is that it doesn't have very high capacitance. It's tiny, and so that means that you can buy your way into high efficiency by adding more conductivity. You don't usually think in terms of conductivity. That's in the units of Siemens, right, is conductivity. But you usually think in terms of RDS(on), resistance, and ohms. But if you're thinking about conductivity, the more conductivity you have, the more capacitance you have. And the capacitance is bad because every time you switch it, you discharge these capacitors through the internal resistance of the part. And that just burns the energy and makes your device hot. So the loss in the switch, in a switching power supply, is there's a COSS times the voltage that's across it squared, and then there's a times the frequency that you're switching at. And then there's a corrector for dimensions you divide by 2. So you can see from FCOSS V squared over 2 that V squared, that's pretty powerful. So if your voltage goes up, and that's the input voltage, so your 110 volts rectified or your 240 volts rectified. COSS is the bad parasitic that we talked about. F is your switching frequency. And so it's a nasty little equation. And what you get out of it is actually better perhaps described on this graph. Here's the Here's a graph of the power loss in MOSFET. If you have a bigger MOSFET, the red curve is your conduction losses. So the bigger it gets, the more conductivity you have, the less conduction loss you have. The blue is the switching loss. And as the device gets bigger, the switching loss goes up for constant frequency because you're discharging this capacitance through the energy in the capacitor through the RDS on every switching cycle. So that gives you a kind of total power. There's a little bathtub curve, not a bathtub, it's more, it's a bowl. You get this kind of bowl-shaped green power loss with device size. So what that means is that for any particular frequency you choose, any designer power supply, that's the best you can get, and you can't do better than that with a MOSFET. You've either got to change the topology of the power supply and take care of the parasitic some other way, or you got to change the technology of the MOSFET. So that's what GaN does for you. Let me see if I can. Yeah, so what I was saying earlier on is that the switching loss in GaN is very low because the capacitances are small. And what that does is it moves this curve down. Right? So your losses are, you can go with a bigger chip and get lower losses, and that means that your efficiency is going to be higher. And that's the trick with GaN. That's it. It's that simple. It resets where you can play in power supply efficiency. And that's why we're using it in all the new products that we're making. We're using our GaN device.
Right. So just, sort of condense some of these ideas together. Reducing conduction loss and switching loss would be ideal, but it's easier said than done. Sometimes the answer is a better transistor, right?
Yeah, and that's the very simple secret of why GaN works. Now, it comes up with a lot of baggage, right? Because GaN is new and people are a little bit scared of it. So one of the things that we've been doing is working very hard to make it accessible, so you don't have problems driving it. You don't have problems with reliability and the quality of the product. We've put it through the ringer, and we've shipped a lot of it. At this point, we don't get field returns that are any worse than any other kind of field returns we get. It's the very solid, robust technology at this point. The spec we put on it is 750 volts, which is quite high for an offline power supply. It's a little bit more than you need in most cases, but it provides a little bit of extra reassurance for the people using this for the first time that this thing's a robust material.
Right, and let's talk a little bit about GaN from that high level. As you already mentioned, maybe people are maybe a little bit scared of it still. GaN as a concept has been around for quite a long time, and you've been talking about these benefits, and those benefits have been quite well known as well. I mean, obviously, it's much more tangible now than it's ever been before. But from a theoretical standpoint, we've known these things about this semiconductor material. So my question here has kind of two parts. One, what are the obstacles and concerns that are kind of standing between engineers and the GaN solutions that you're offering here at this point? And two, what do you think it's going to take for them to get over those obstacles and concerns?
Yeah, I think most of the concerns are around just a lack of familiarity. People are so familiar with silicon. I mean, we've been using silicon for 70-something years, right? And you bring up a new material and you say, this one's better. People want to know, well, where's your 70 years worth of experience with this thing? And am I going to have, is it going to vanish in a puff of smoke after just 5 years of operation? Are my customers going to be happy with this thing? Is it going to last? Is it going to... And that's what most of our customers' main concerns are around. And what we've done is we've shipped an awful lot of it at this point, and we've been doing that since December 2018. And so we have quite a bit of experience with it. Guys who came before us in lower voltage applications, I'm thinking about EPC, they've been working in this area for probably 10 years before we were. And they have a lot of experience of it, and they've done a lot of testing on it. And then there are a few other companies out there who've done some work with GaN. TSMC has a GaN technology that some people buy. What we're seeing is that if you do the testing and you run the JEDEC recommended test, and then you exceed the JEDEC recommended test and leave things in the oven for 2x the time, 3x the time, you kind of eventually, as an engineer, just feel this stuff's okay. And that's where we're at with it at this point. Is it doesn't break. It's solid stuff, and so that's why we felt comfortable offering it to our customers. We have a reputation for reliability, robustness, and quality of the product, and we didn't want to put that in jeopardy by shipping something that was dodgy. So we did our testing, and we convinced ourselves that we would use it.
Yeah, that makes a lot of sense, and I think you put that very nicely. That idea that engineers are, by and large, really big fans of trusted solutions that actually work. So maybe we're getting into this age now where GaN isn't necessarily, as it becomes more available, as it becomes more affordable, or now in this period where we're not waiting for it to hit the market, we're waiting for it to gain that trust and familiarity. So let's empathize with that engineer real quick. At what point in the design process do you envision this theoretical engineer that we're talking about? At what point are they looking at making a decision about between silicon and GaN, or GaN and another semiconductor material?
Well, I haven't seen our latest metrics, but 3 or 4 months ago, we did a little study on how many people are buying GaN from us and for what purposes. And it was something like 90 separate applications. We have a CRM system, everybody does, and the CRM system captures a bunch of information about what people, who people are, obviously, and then what are they doing and what they're buying. And we got something like 90 separate applications. So it's not 90 customers, we've got more than that. It's 90 application codes. And it's everything from refrigerators to adapters to some more exotic military applications. There's a whole bunch of stuff out there where people are using GaN. And so the first and simplest reason for somebody who hasn't tried it yet to try it is everybody's using it. And so it has benefit. And if you don't understand it and you don't understand the benefit, you stand a pretty good chance of being left behind. So at this point, I would say if you're in the power business, you really ought to have something that uses GaN in your development or in production, preferably in production, but certainly in development. You should be seriously considering your competitiveness if you haven't understood what GaN can do at a very detailed level, and that detail needs to be something like you've gone through a product cycle with it to understand what it can do. Because it's not just the efficiency we've been talking about. It's not just the energy savings we've been talking about. What it does is you can wander down to your mechanical engineering guys and say, if I can get, if I can half the thermal budget, what can you do? And the mechanical engineers can say something like, well, we can take the fan out. We can close at the slots, so we don't need to have pollution level 3 anymore because there are no holes in this thing anymore. We can radiate through the case, so there's no airflow. And that means less dust. There's no ingress for moisture. You don't have to worry about whether ants are getting at it and short out the power supply. There's so much benefit if you can fully enclose something. So there are things that you can do like that, and that's what customers are using GaN for. They're finding ways to completely change their game, not just at the electrical level, but at the mechanical and product level, and making better products that are higher utility and save so much money at the system level. If you can get rid of a fan, and you don't need to machine the slots. You don't need to have the fan. You don't need to have a guard on the fan on the slots to stop kids sticking their fingers in. There's a whole bunch of stuff that happens if you can leverage a less thermal budget.
Mm-hmm.
Sorry, I ranted on that a little bit, but it's important. I think people should consider the mechanical aspects of the design and go beyond just the electrical performance.
That's excellent advice, I think, in general. I'm watching your time, and I know that we have quite a lot more conversation to be having here. I'm really excited. I have the advantage from my eagle-eye view here that I know there's some really interesting slides coming up. So if we can switch gears very quickly here, I believe we wanted to talk a little bit about some of the applications that GaN is really commercially beneficial for.
Well, yeah, this is actually one of the things that you can do if you're using GaN, and that is this is a little bit another soapbox of mine, and that's getting rid of the heat sink. Because if you think about it, what a heat sink is doing is it's coupling wasted energy into the world. Right? So first somebody's got to generate it, and then you're going to waste it. So a heat sink is a tool in the power supply business. We use it because we got to keep the components cool. But if you generate less heat in the first place, you don't need to dissipate it. Right? And so what a heat sink is, it isn't it's a symbol. It's a symbol of waste. It's a
like
if you have a heat sink in your system, you're wasting energy, right? Mm-hmm. That's it. So there are alternatives, and the alternative in the case of one of our products here is you just heat sink directly to the PCB and let the PCB be your heat sink. But you can't do that if you generate too much heat, because when the PCB gets too hot, the components don't stay cool. And so you can't do that. We have 3 GaN devices in this particular adapter. It's a tiny little thing. It's a measurement 44 by 44 by 12, and it's just checking out 60 watts. So 44 millimeters for those who are sort of imperially challenged like me. It's an inch and a half, right? So it's an inch and a half by an inch and a half by half an inch. Big. It's tiny. And that's doing 60 watts. And there's no heat sink in it. It's just heat sink directly to the PCB. And that's because you don't generate any heat. It's a fantastic little design.
And this is, just for context here, this actually came out, was that this May, 4CZ came out?
I'm sorry, I missed what you said.
Yeah, I was just, doing some friendly stalking on the Nswish 4CZ.
It came out
this
we
May,
launched that,
right?
This year. Okay. Yeah, we launched that this year.
Awesome.
So that's new. And so, getting back to the oh, there we go. That's a nice little demo of how big it is. It's tiny. I think as engineers, as power engineers, we ought to sort of, there's all these challenges on YouTube, right? Like throw a bucket of water over your friend or something. But I think we should have an eliminate heat sinks challenge. I think engineers, when you do your next job, think about how to get rid of the heat sink. There's nothing good about this thing. It's kind of attractive, actually. I like the look of it. Kind of, there's this sort of tree-like structure associated with them. So aesthetically, I said they fail the progress aesthetic, but they are actually kind of visually kind of nice. But they're a symbol of waste, and they should be eliminated. Death to heat sinks, that's what I think.
Well, I love that. Death to the heat sinks. Throwing some serious shade daily here. So just very quickly. It's a pretty intense challenge. If you can imagine someone in the audience who is like furiously naysaying at the screen right now, what might objections be to this sort of challenge, this type of concept? Is there a case for heat sinks that we need to consider here?
I don't think so. I don't think heat sinks have I don't think they have a lobby group, right? I mean, they're just a way to use up metal and burn energy. There's nothing good about heat sinks. I'm not going to defend them.
I agree with you that there are some that are very aesthetically pleasing, but
yeah, they look nice. Put them in a museum. They belong in the motor or something, right? modern art museum, or just any museum, really.
I love that. And it's worth mentioning, just to kind of underline your point there, that best case scenario, the heat sink ends up with a recycler, right, at the end of life, and there's still additional waste even if you do recover it. Right? So, all right. So I have to say, we do have some really great questions coming in the back end, but I want to make sure that we have time to have this conversation that you've set up at the end here. It's a really interesting concept. Do you mind popping up that next slide and telling us what you mean?
All right. Okay. So this is something, the undiscovery of fire, and this is an observation that I made. I don't know how it came, but if you think about it, we've been burning stuff for a long time, right? I got a little image here of somebody lighting a cave and cooking back 100,000 years ago, but you might go back like 3 million years, or however long it's been that Homo sapiens have been burning stuff. And I think that we're coming to the end of burning stuff, which is an interesting thing. Over the next 50 years or so, humans are going to stop something, going to stop a practice that we've been engaged in since the dawn of our existence, and that's burning stuff for heat, light, and motion. So, even 1,000 years ago, there was I found a little thing of some guy cooking, and it's a bunch of people lighting their way on let's say, going somewhere. Even 100 years ago, steam trains still burning stuff, and we lit our homes with gas. I don't think there's anybody alive today who remembers gas lamps in their house. I mean, that might be a bit of a gone thing. But today we're still putting gas in our vehicles, right? So gas cars, we're burning stuff. It's a fancy way of doing it. You stick it inside an engine and you run the engine, and it explodes stuff. But it's still burning stuff to get what we want. Here's the first guy who figured it out. This is Edison with his light bulb. Right? So for 100 years or so, people have been working on not burning, or ways of not burning stuff to get what we want. But even now, there are folks out there who are still using charcoal to cook, and there are folks here using gas to cook. But it's not that far. It's not different. It's still burning stuff to get what we want. But if you think about generating energy now, it's solar and wind. There's no burning anything in solar and wind. Think of an electric vehicle. You're not burning anything in an electric vehicle. So there's a process going on where we can eliminate burning pretty much anything. You can cook with electric. I don't know if you've been cooking with electric for a long time. But the hard one, I think, is flying. I think flight is going to be a lot later. You still need jet engines that are going to burn things because of just the energy density of it. But, we are, after 3 million years, this generation of engineers, and perhaps the next generation of engineers to finish it off, is going to undiscover fire. I think that's pretty profound.
I agree. I think it's a really powerful sort of slide, and I love this concept of burning stuff to get what we want, as it just puts it so succinctly. I do have to ask very quickly here, Doug, you have to forgive me. On this slide, there's a very specific date here, April 5th of 2063.
Oh, that was for the nerds, because I've mentioned this to some people inside the company, and they go, oh yeah, but rockets, you still need power to get your rocket out. So this is for Trekkies. Actually, I'm a Trekkie as well. So this is for Trekkies and other nerds, and this is the Phoenix, right? So date of first contact is 5th April 2062. So this is to show, we probably still need to burn stuff for rockets. This is a kind of the exception that proves the rule.
I am so happy that that's what that was. We were looking at the slides earlier today, and we're just sort of like, what does this man know that we don't? That's very wholesome. I like that. All right. Well, just a really quick thing. I happen to know that it's an important, it's a near and dear topic to your heart. I just wanted to make sure you got a chance to, as we're talking about this, moving away from burning stuff. The concept of EWaste is also extremely important for this GaN conversation. Would you like to talk about that for just a minute?
Yeah, and I think that goes down to just building things that last longer. This slide here, I think if we go back to get away from burning stuff for a minute, let me go to that one. This power supply design that we talked about briefly is a USB PD power supply. So the fantastic thing about USB PD is it can go from 3.3 volts. The output of the power supply can be from 3.3 volts all the way up to 20 volts, and the committee is busy extending that out, I believe, to 48 volts. So not only do you have to, as a designer, manage from 85 volts in quite often up to 265 or even 305, you need to be able to operate across that range. You've got a couple of, you've got more than a decade, a digital decade of dynamic range on the output also. It's a very, very challenging design. But what that does for you is it means that you can use this power supply for your cell phone, you can use it for your laptop, you could even use it for powering a TV. There's almost nothing in your house that's electronic that couldn't be run from a 5 amp 48 volt source. TVs and entertainment systems and anything that charges from batteries. I mean, even vacuum cleaners these days are starting to be battery operated because you don't want to have to drag a cord around your house. So I think there's a case to be made for pulling the wall plates out that are these AC wall plates and replacing them with USB PD wall plates. The power supplies are tiny. You could essentially a de facto DC bus, and I really feel like this is the next wave of action that can happen in reducing e-waste by moving the adapter into the wall, making it a piece of infrastructure, and then you don't need power supplies in the equipment either, right? Because you can run off the directly. You can tell the wall plate what voltage you want and just get it directly. And then you've only got the little bits of DC-DC conversion to do to condition the energy for the electronics in the system. So I think we are addressing e-waste also by being efficient, building efficient products, and then initiatives like USB PD.
Well, I think that's probably the best way you possibly could have answered that question. Is specific and actionable, and I'm glad that we got a chance to talk about that really quickly. So if it's all right with you, Doug, we'll actually start answering a few questions. We've got about 10 minutes here. Let's do it. I'm going to remind everyone in the audience, if you'd like to submit a question to Doug, there's a Q&A widget at the bottom of your screen. If we don't get to your question today, don't worry. The Power Integrations team will be able to get their hands on that, and they'll be able to reach out to you individually. But let's see how many we can get through right now, because we've had some great engagement throughout. Let's start with this one. Let's see, is GaN used above 1 kilowatts in power supplies? I think that's the best way to ask that. For example, in gaming PCs where power supplies are up to 750 watts, it's very high power.
Yeah, that's a good question. We don't have anything at that power level at PI, but I do know that there are other GaN companies out there who are looking at that. I don't know if anything's in production yet, but I believe it's possible. There are several companies with very competent GaN transistors that we tend to integrate the GaN into a component, into a subsystem, because we want to make the GaN easy to use. When it's just a device or even just a kind of Dr. Moss type GaN with a driver and a GaN together, they're still very difficult to use, and you require a lot of external components. You've got to worry about fast edges and parasitics, and and so on. But I believe that it is possible to use GaN in these high power power supplies, but I can't put my name on a part number.
Mm-hmm.
I can't
No
put
worries.
a part number.
Yeah. Well, this one actually started with a very kind compliment. Just a quick mention that this person believes that this presentation is second only to the keynote with the 2 astronauts in it from the other day. So that was very nice of you. Thank you, commenter. You and astronauts, Doug.
Well, I got a space rocket in at the end. I got a rocket in the end. I get credit for the rocket.
Yes, I think that really put it into the same tier. So this person's question is, will we get the sort of detail that you've been talking about throughout this presentation on data sheets? And if so, are there features or terms that they can look for to have this level of consciousness for efficiency? I think it's a great question.
Hang on a second. I got to read that question to understand it.
Yeah.
So detail. Okay. So the data sheets that we provide are very dry documents. They're intended to completely describe the product, but they're not light reading. There's a lot of very a lot of detail in there, and there has to be so people can use the products that we make. The sort of background information that I've been talking about today, and the reasons why we did things, and the general utility, that tends to reside more on our website in articles that we write and application notes. So that's where I would look for the more background information.
Perfect. All right, we've got several more here, so let's see how many more we can get through. This person was wondering if you could please briefly comment on how to trade off efficiency and power density.
Okay, yeah, that one is a very, it depends kind of a question, but essentially, here's an example. If you have a transformer if you make your transformer a little larger than it has to be, then your flux density is lower. So the flux swing in the transformer is going to be more beneficial than if, from a flux density point of view, than if you squeeze a transformer very small and go for very high flux density. So that's an instance where you can make something more efficient and big rather than less efficient and small. Another one is with bulk capacitors, for example, where if you allow your input voltage or the voltage that goes to feed the flyback to get low, then you're going to your MOSFET or your GaN device inside the main switch is going to have to work harder, and you're going to exercise the RDS on, and so your efficiency will go down. There is a way to fix that, and we have a product called MiniCap, which is actually called out on this design. And what that does is allow you to use small capacitors without the penalty. And so, there are ways around all of these things, and that's why it depends kind of a question. But yeah, you can make things big and efficient and small and inefficient, and eventually you bump into this problem of thermals. If you make something too small and too inefficient, then it gets too hot. Right.
Well, that was a great answer. Thanks for tackling that, even though it wasn't super easy to do a one line for it. Maybe this one will be a little bit more straightforward.
It's one of those ones where people spend a lifetime working on that one and puzzling out the how to handle it.
Well, we'll wait for you to write the book about it, Doug, about that. when you release your book on power density and versus efficiency. In the meantime, this next commenter is asking about which GaN type you guys are using. Is it E mode or D mode?
Okay, so this is a forbidden question. We don't like to talk about it very much. We do it differently than other people do. I can tell you that. We co-pack the GaN with a silicon device that's the controller inside our package, but we don't actually reveal much about the GaN technology that we're using. And there's a very good reason for that. We believe we have a substantial technical advantage from the way we operate, and so we've chosen not to talk about the details. But please be assured that it works really, really well. And I feel a little bit constrained because I kind of want to tell you. Right? I really want to tell you.
I know.
I can't tell you.
The urge is strong that we won't press you on it. So let's see if we can knock out a few more questions here. If anyone needs to drop off, I know this is the end of the hour, but we want to make sure that everyone gets the full hour of presentation, full hour of Doug. So very quickly here, what about standby and no-load power with GaN-based switching circuits?
Doesn't make any difference, really. GaN is lower capacitance, and so you will get lower losses than the equivalent silicon circuit. But because there's so much else changed when you use GaN, you're using usually at a higher power level, or you're trying to make something smaller. So you're almost never in a situation where you've got a silicon equivalent next to a GaN equivalent, and the few milliwatts of difference just get swamped. So I think from the point of view of a designer, you can just say no difference. Now, not all GaN is the same. Some GaN is very leaky, and I think you'll find that some of the standalone transistor-based GaN products are very, very leaky. And so they may show far more quiescent current draw, but our GaN is not leaky. It's when it's off, it's off. And so we see no difference for our products.
When it's off, it's off. That's awesome. All right, let's move on to why is GaN proliferating in the adapter and charger market so quickly? Is it being used elsewhere?
That one is a good question. So it's because that's where the benefit lies. If you think about it, it's right here, this USB PD adapter. If you've got something that needs to be mobile and needs to be powerful and isn't part of the user experience, or if it becomes a little bit part of the user experience, then you need it to be small and out of the way and kind of sexy. So it just seems like the adapter guys have grasped hold of GaN and gone for it in a big way, and they're getting a ton of utility out of it because they can make their products smaller and nicer. I mean, a lot of times a power supply is we're kind of like the goalkeeper, right? The power engineers. Mm-hmm. Nobody notices you unless you let one in, and so nobody notices the power supply until it stops working. Well, in adapters, people do notice the power supply. They get value from the GaN, and that's why they move to GaN first.
Mm-hmm. Well, let me also just mention, very kind audience here. Thank you guys so much. We've got another person that said they're very much enjoying your presentation. So just wanted to toot your horn there, Doug. Another question for you here. GaN devices allow the designer to increase switching frequency and reduce transformer size. Is this where the GaN benefit is the most important?
Yeah, I think it is important because once again, it speaks to making the adapter smaller, right? If you can get down a core size or two, it allows you to make the adapter a little smaller, and that speaks to value. So yeah, it's all part of the value package that GaN gives you.
All right. Got a few more questions here, so let's keep rolling for as long as we can here. Will emerging efficiency standards force designers in multiple industries to switch to GaN? Force it.
Well,
you mentioned before that they might get left behind.
Word. Yeah, force is a strong word. I would use encourage. I mean, one of the things that we found with the European labeling system is that most of the appliance makers in the world have said, no, we really want to have an A on our label. We don't want to be a C label guy. We want to have an A label for efficiency. And so they're being encouraged to switch over to GaN, because every watt or two they save gives them a better chance of being further up that the pecking order on the labels, so that they get a B or a B plus or an A on the label, and that has a real marketing benefit with consumers, because particularly in Europe, consumers are very climate conscious and efficiency conscious, and they want the better product. That's why the labeling system really works.
Yeah, that's fair. Well, let me take this opportunity to announce the winner of our giveaway very quickly here as we wrap up. So congratulations, Amanda Buchan. So Amanda, our team will reach out and make sure you get your hands on your prize package. Thanks so much for attending today. And before we sign off here, Doug, let me just ask you, is there anything else that you'd like to leave the audience with in terms of final thoughts?
Final thoughts? Yeah, only to thank you guys very much for taking time to listen. It's been a pleasure to do the talk to Kate and everybody. And if you have any questions on GaN or the website's available. We've got myself and other folks who live and breathe this stuff, and we're happy to talk about it all day. So reach out and let's talk. Perfect.
Yeah, and let me just echo that. Thank you to Power Integrations, and thank you to everyone attending here today. And thank you, Doug. This has been such fun. It's been a great conversation. And just so everyone's aware, you will be able to access this entire thing on demand for whenever you like later on. So with that, I think we can conclude here. Excellent job, Doug. And I hope that you guys have had a great day 3 of Industry Tech Days 2021. We'll look forward to talking to you again bright and early tomorrow morning for day 4. Have a great night, everybody.
Thank you.